All right. So we're going to start off where we kind of finished off last class, because I wasn't totally done talking about standard deviation and finding it, those type of things. So first thing I want you to do is take those numbers and put them in order. Just going to do it a little bigger. Oh, shoot. That's not what I want to do. Reload. There we go.
Front back, right?
Yeah.
Hey, maybe before.
Six. 91. Okay. In order. All right. Okay. Find me my mean.
I would look up at the wrong moment, so I couldn't remember if I added 96. So I was
Yeah.
like, did I add it twice? Oh no. How many decimal places?
All right. So here is how you figure out how many decimal places to go. You always go one more than the data that you have. So if my data has no decimal places, I would go one more than that. So my mean in this case is 89.4 because it's 4167. All right. Now I need you to find my standard deviation. And I told you I was never going to make you do it by hand again. So you are more than welcome to use Google to find a standard deviation calculator, or if you go to my website, I linked it. It's on the post for the class for last class. It's calculator.net is the website that I use. And finding my standard deviation. Yeah, it should be under stats. Yeah, it should be the very first post. It should say standard deviation calculator. You click on that link, it should take you right to the. Yes.
Is it a population or a sample?
This is a population because we have it all.
Aha. Wouldn't a sample, you would be given this and then I'll select something.
Or it would tell you it's a sample.
Okay.
You can assume if they don't tell you it's a population, if they would tell you it's a sample. When you do it, you should get 6.8. But I want you to be able to do it. So go to the website, find the thing, actually do it so you know how to use this and get the same answer that I got. Actually, sorry, it's 6.9. I got to round up.
Rounding, not rounding.
Rounding up 6.9. Sorry.
Oh.
If you can't get it, tell me and I'll come help you get it. So you can do this because you're going to have to be able to do this on the test next week. So I want you to be able to do it today and be able to get it.
We're allowed to use our phones for.
Yes.
Yes.
Yep.
Okay, it's giving me a lot of numbers. Oh wait, never mind.
The standard deviation should be the very top number.
Yeah, I managed to read right over that.
Yeah. Yeah, it gives you a whole bunch of stuff, but standard deviation should be the very top number. bakersmathclass.com. This is my site. And when you go to statistics, that's where all your notes will be and all the videos of the classes will be. So,
I went to like the important links thing.
yeah, I don't think I put it in there.
No, it's not in there.
Yeah, because I had, when I created that page, I didn't have a stats class at that point. So, and there's your standard deviation, and it also does give you your mean to verify your mean is correct. All right. Okay. Everybody have it able to get that? Okay. You're going to take the exact same numbers. I want you to add 20 to all of them and find me my mean and my standard deviation. Okay. Add 20 to all those numbers. Same thing. Find me my mean and my standard deviation.
I'm saying, can you just double check these numbers?
It should be on the board too. I just did it. Oh, it would be on the board if I actually shared the right page. There we go. Now it's on the board. And if you're smart, you realize that when you did the standard deviation, the last one, it gave you the mean. So you don't calculate the mean, you just type it right into that computer and get both of the numbers without having to find the mean first.
Right. Well, now you said that hardly. So.
On purpose. I did say it actually when I showed the last one. I'm like, and it shows you the mean, but some people didn't catch that.
Some of us are.
What do you notice? What's the difference between the mean of this one and the mean of the last one? It was just plus 20. So if you added the same thing to every one of them, the mean's literally going to change by the exact same thing. What do you notice about the standard deviation, though? They're the same. What is standard deviation telling me? The spread. If I added 20 to every single one of them, did the spread change? No. So that's actually important to understand, that standard deviation is looking at the data, but you can have two different data sets that have the exact same standard deviation. That is possible. Okay? So don't just go like, wait, I've got that standard deviation before. It's possible. It's looking at how far the data is spread. So in this one, the spread didn't change. So my standard deviation stays the same. All right. So when we talked at the very end of last class, we started talking about the 68, the 95, and the 99.7, right? Remember that vaguely? Okay. So duplicate the slide real quick. Don't want to duplicate, delete, thank you. Want a blank slide. Just this. All right. So if I was to look at a bell curve, which is a horrible bell curve, that line kind of is in the middle. This is my mean, correct? And my mean for this data was what? Okay, so 109.4. My standard deviation was 6.9, correct? Okay, so one standard deviation out from that. I'm going to minus 6.9, and I'm going to add 6.9. So what do I get? So if I add 6.9 to my mean and subtract 6.9 from my mean, what do I get? Huh? No, you have to do one way and the other one the other way.
Oh, okay.
So you're doing both, not to the number at the same time. So it's 109.4 plus 6.9. Okay, and what's 109.4 minus 6.9? Okay. So that means that those six numbers, right? Is within one standard deviation of the mean. Correct? Okay. I have 12 numbers. That's 5 of them, or 6 of them out of 12. So it's about 50% of the numbers. But I said it was 68% of the numbers, right? Should have been there. Okay. So when you're looking at standard deviation, and when you're looking at data, and when we're looking at that 68, the 95, and the 99.7, and the normal bell curve and everything else, my data has to be normally distributed. I've only got 12 data points here. I don't know if this is normally distributed. Okay. It would have to tell you it's normally distributed to be able to do those extra steps. You can find standard deviation stuff, that's fine. But you need to have it be normal to be able to come up with all the rest of that information afterwards. Okay. As long as you have a data set that has at least 30 values, 30 or more, you pretty much can assume it's normally distributed. And you can do all this work with it. Anything under that, you really have to know if it's normally distributed to do anything with it. Okay, does that make sense? So 12 data points just basically isn't enough to fit that mold of the 68, the 95, and the 99.7, and everything we're going to do after this kind of point with the bell curve. All right. you kind of need more data points for it. That's why when we're looking at data, we normally collect hundreds of pieces or thousands of pieces of data. We don't collect like 10. Okay. It would just have been a lot longer for me to tell you to type in 30 different numbers into the calculator to do it. So that's why we don't do normally that much stuff when we're looking at it in class. However, we can look at problems that have already been basically done for us. So we've got a manager of local dining calculated his average daily sales to be $4,500 with a standard deviation of 750. So they've done our mean and our standard deviation already for this one. So I want you to basically do my nice little bell curve that I had from last class, which I'm going to pull up now because I don't feel like searching on the internet for it again. So we've got, what's this one? Mean 4,500. SD is 750. So I want you to fill this. So your mean's going to go in the middle. 1 standard deviation, 2 standard deviations, and 3 standard deviations out. So you're just going to basically keep adding 750 this way, minusing 750 that. So that would be 1 standard deviation. 3750 into 5250. So keep going. Find me the second one and the third one. All right, which range is going to be 68% of all of his sales? A range is a beginning, a starting and an ending. Correct. Okay, 68% is 1 standard deviation. So that's 1 jump on either side. So from 3750 to 5250, 68% of all of his days would fall within that amount. Everybody get why? Everybody understand that piece? So if we're looking at his sales for the entire year, right? 365 days, 68% of those days would fall between $3,750 and $5,250. What about 95% of them? Yeah, between 3,000 and 6,000. And then if we wanted to look at 99.7 of them, which is basically all of them, it'd be between the 2250 and the 6750. So if his data is normally distributed, the lowest day that he'd probably expect over the course of the year would be around $2,250. The highest day that he would expect over the course of the year would be probably around $6,750. Okay. Because after that point, we're talking about 0.3% of all the actual values. So it's like 3 out of 1,000 days, which is about a day out of a year. Because 365 times 3 is more, just over 1,000. So there could be one day out of the whole year that's outside of that range. Okay. Yes.
Number in my thing. What's the middle number for the 2 standard deviations? What percent is that?
95.
Like,
Yeah, it's 68.
9%. I'm like, that's
Yeah, 68, 95, 99.7. What now, when you're looking at these, we can have a variety of information pulled from this. So if you notice, this bell curve is broken down into the pieces. So like this piece right here is 13.6% of all the. This piece right here is 2.1%. So I could say, what percentage of days will be less than 6,000? What do you want? No, less than 6,000, not more than 6,000. So less than 6,000 will be going this way. So I would add up all of them. Okay. Or I could just add those two and subtract 100. That's what I would.
Add the 2.1 and the 0.
Right. You get 2.2 and subtract that from 100, and you get 97.8. That's a little faster than adding up all of them. So I have a 97.8% chance that I'm going to make $6,000 or less. The converse of that is I have a 2.2% chance of making more than $6,000. All right. Does that make sense? Okay.
Yeah, so Z-score popped up in
On 4.3, yeah. Which I don't know. This is that Hawks thing that makes no sense. Like, because it shouldn't have been in 4.3, it should have been in 4.2. Or what was there should have been, it's, yeah. Because it literally goes to standard deviation and stuff. It doesn't go to anything else.
Yeah, that was like so confusing.
Yeah,
I was trying to
it's-
figure out what it was.
Yeah. This is why the more I look at the book, the more I'm like, I'm just going and I'm putting the stuff that makes sense together and not necessarily totally following the book. I haven't checked chapter 6 yet. And then I'll redesign how I did it. The nice thing is 4.2 did not have anything for mean absolute deviation, so you didn't have to worry about that.
You said that like a Hawks, it's more participation than specific grade, right?
Yeah, that's at 20. No, that's at 20%. That's the homework. That's at 20%. So
It's Hawks is a hot list.
Yeah. That's what I said. The more I play with it, the more I'm realizing that. And to be fair, I just took the curriculum from what the person that has been teaching this one in Hawks did. So next time I teach it, I'll fix things up my way. All right. So Z-score is actually a very important piece of information. What Z-score does is it tells me how many standard deviations away from the mean that specific number is. Okay. So remember we were talking about how Like a doctor can figure out where your weight is compared to everybody else's average weight. Say you're in the 93rd percentile or the 94th percentile. That's in essence doing a z-score. They take the z-score and then they convert that into a percentage. And they say you're in this percentage. Okay. If you have your book, there's a Z table in the back. Most of you don't have a book on you or it's online, which isn't going to be very helpful for you to look at right now. So I will throw it up on the board. This is what a Z table looks like. Whole bunch of numbers. Don't worry about it. We're not going to actually use this yet. We will use this down the line. But what it is this is telling you how many standard deviations it is, and this is telling you the percentage. So one standard deviation, right? Positive one standard deviation. If we look at this, if we're right here, what percentage is underneath that? So if you add up all the numbers from here all the way down, what percent would you get? Or you can do it the other way if you want.
So that would be adding like the 4,500.
No. The percentages, not the number. The percentages. So add up the 34.1, 34.1, the 13.6, the 2.1, and the 0.1. Okay, so 84. So one standard deviation would be 84, right? If I go to 1, what's the number right next to 1? 0.84. Oh, you're not in that. I'm not on the screen. There we go. What's the number right next to 1? 0.8413. That's 84.13%. So the Z table will tell you exactly what that percentage is. So if you're at 3 standard deviations above the mean, you're in the 99.87, so the 99th percentile. Because you're at 99.87%. Okay?
Are we going to want access to these tables?
No, you'll not need access to this table for this test. I was showing it to you because I wanted to make the connection between what Z scores are and what we were just talking about a second ago. You will use this later on in other chapters, and I will have this printed out and given it to you on the test. So don't worry about that part. All right, so Z-score is basically telling you how far away from the mean you actually are. Okay? So to find this, these wonderful little symbols here. Z is the number, the value you want, minus the mean, divided by the standard deviation. Mean is that funky little u. Standard deviation is it's actually mu. It's the Greek letter mu, which is M for me. And that's the small omega is the standard deviation symbol. They're Greek letters.
Okay, when you're due for an eye exam,
Yeah.
my vision is so bad.
So call up your eye doctor, tell them to put all Greek letters on your menu. Got it. All right. So that's how we'd find the Z-score. We take the value minus the mean and divide it by the standard deviation. Everybody got this down? Okay. I'm not going to use those. I'm going to actually give it. These are heights, right? I need the standard deviation. I don't know this one off the top of my head. Oh, this is actually really cool. Not what I want, but really cool. I'll show you that in a minute. I need the number. Like, uh, I'm just going to make it up in a minute. Get it? I'm just making it up. So the mean of babies being, or well, we're going to assume these are girls. So the mean is 49 centimeters. It's not for this data, but I'm going to use this data to do something else. And the standard deviation is 25.5. So cut that in half. So 4.5, 2.25. Yeah. And the standard deviation is 2.25 centimeters. Okay. I want you to calculate the z-score for baby number 3. So you're using that number right there. So how do we calculate it? Correct.
So the value would be what?
48.9. So the Z for baby number 3 is 48.9 minus 49 over 2.25. And what do we get?
What mean, is that a 49 or is that a 44?
49. That's a 49. So 0.04. So that's my z-score. What's the 0.04 mean? So this baby is basically right in the middle. Oh, you're right. It is. So the baby's basically still, it doesn't make much of it, right in the middle, right? So it's because remember, 0 standard deviation is the mean. As you get a higher positive, you're going further and further to the right. More negative, you're getting further and further to the left, the smaller, right? Does that make sense? Those two directions? Okay. What's the Z? So find me the z-score for baby number 1 and baby number 8. We'll do the two extremes. One and 8. Which baby is more extreme? Baby number 1. Their standard deviation is farther away from the mean. It's more negative, that's fine. It's just, but it's farther away. So that's a more extreme case.
And then on the graph, it would fall under the second one over. So like,
So yeah, if we were looking at here, the negative 1.74 would be like right over through here, right closer to the 2. And then the 1.65 would be somewhere over here, probably closer to the middle, just a little bit more than 1.5. No problem.
putting it there helps.
Yeah, no, that's fine. This is the chart you see at the doctor's office. Now, this is one of those things that now you actually can start to understand what it means. The green line in the middle is 0. 0 what? No, 0 standard deviation. Okay, so that green line is your mean. So that's your mean. They don't put 1 standard deviation on here. I don't know why, but they put 2 and 3. So you can start to see the extremes under the outer edge. That's 99.7% of all the babies should fall between those 2 black lines. If you're outside of it, if you're low, that's a major problem because you're really low birth weight. And if you're high, that can cause other issues down the line. What's the? Hold on, I'm going to find out what the. Does that? So I have some people who work in healthcare. Do you know what the baby's weight is that has to go into NICU? um, 3 pounds 5 ounces, but I need it in. Oh, that's. I was looking at. This is yeah. I was looking at the. This is height, but yeah, it's 3 pounds 5 ounces or 1,500 grams. So let's see if I can actually find my chart again, and I can show you the weight chart. Weights. So here, this is the weight, and it's weight to length, because obviously if you're longer, you're supposed to weigh more. And this one does have the same things. It's got the 1 standard deviation, 2 standard deviations, and 3 standard deviations. So, and 2 kilograms is at the very bottom here, and 1,500 grams is 1.5 kilograms. So that's even below that. So if you're looking at that, what percent is down here under 3 standard deviations is 0.1%. That means if you're weighing less than 2 kilograms, you're in the 0.1% of all the babies being born. Okay, so that's why they have to look at those types of things. So you can start to see how this stuff is used, which I think is kind of important. And yes, it's looking at more like the weights and heights and stuff like that, but this is one of the easiest places for me to show you this exactly how it's being used. So, and where the z-scores and stuff come into play, because that's where they look at those numbers there. All right. Last piece. Last thing we're going to talk about with this before we go to the test next week. Coefficients of variation. So your coefficient of variation is going to be your standard deviation divided by your mean. So it's your standard deviation divided by your mean.
Anything as CV, that standard deviation.
So CV is coefficient of variation. That little
Okay.
U or that the O symbol, that's standard deviation. The mu is your mean. Mean. Notice we do have two different formulas. They're actually the exact same formula. The symbols are the only thing that are different. These are the symbols that you use for population. Those symbols, if you're looking at a sample, the S is standard deviation and the X with the bar over it, that's the mean of your sample.
What's
But-
the stuff after?
Percent.
Percent? Oh my god, I can't see it.
You really do need glasses now, do you?
My appointment is in February.
Oh, God. As long as you can see the cars in front of you, that's all that really truly matters when you're driving. All right, so coefficient of variation doesn't have a unit attached to it. It's not like centimeters or anything else like that, but it allows us to compare two or more data sets. Okay, so it allows us to take some data sets and figure out how we can compare them, like which one is more or which one is less variant or variable than the other one. What are you trying to say? And I can zoom in on it. Yeah.
Oh, I think there's a line for X.
There, yes.
Okay.
So their formulas are identical. The two formulas are the exact same thing. The symbols are different when you have a population or when you have a sample. The first one here is population,
Sample.
and it's standard deviation over mean. It's the same thing. It's literally the exact same thing. Yes, because you want to change the decimal that you're going to get to a percent. All right, everybody got the formula down? Because now we're going to use it. All right, so if you buy anything in the store and it has a weight on it, you'd expect to get that weight in that bag, correct? Or that box. Well, the bad news for you is you don't always get that. However, it does have to be in a certain range, okay? Based on the FDA or the FDA and stuff like that. They actually mandate that it has to be within a certain range to be sellable. Same thing goes with drugs and things like that. Because everything you're putting, when you're using machines are never perfect. They're always going to be a little variation. So in this case, they're looking at two brands of vitamins. One brand of vitamins saying that it has 500 milligrams in it, and the other brand is saying 250 milligrams in it. They've taken a sample. They found the mean to be 500 for brand A and the standard deviation to be 10. And for brand B, they found the mean to be 250 with a standard deviation of 7. The question is we're going to find the coefficient of variation for each one, and then we're going to find out which one is more consistent. Okay? So let's look at A, and then you guys can do B. So all we're going to do for A is it is going to be 10 divided by 500 times 100. That's it. That's the coefficient of variation.
That how would it be written on the test?
Coefficient of variation?
And then
Yeah, so they're going to give you some information for you.
it'll say X and
Yeah, or it'll give the other symbols if it's the entire population. So A is 2%. And now find me B. So what'd you get for B? 2.8%. So which brand is more consistent in their actual milligrams per tablet? A. It's got a 2% variance, where B has got a 2.8% variance. So A is more consistent, even though standard deviation is higher. Okay? If the milligrams were identical and the standard deviation was higher, you wouldn't have to do it. You could literally just look at that. But the coefficient of variance allows us to look at different means and stuff like that to be able to compare. So in this case, this brand A is more consistent based on its advertising. This right here is actually the biggest difference when you look at generic drugs and named brand drugs. Name brand drugs have a tighter tolerance than the generic ones. Same drugs, but it's a little looser on the tolerance. So that's why sometimes people don't get the right effect when they take a generic drug, is because they're more sensitive to that little dip or increase in it. So,
And then, so because that's a smaller number, it's more.
yeah, it's more consistent, right? The coefficient of variance, the smaller, the more consistent it is. Because you got to remember, the mean's not going to change. The smaller the standard deviation, the smaller that coefficient of variance is going to be. All right. Let's do one more. All right, one more. Okay. Which machine is more consistent? Yes.
What is the fraction next to the name?
It's a 1/4 inch bolt and a 1/2 inch bolt.
You don't have to like factor that in.
No. No. But if you look at your mean, that's your means. No, because the means aren't the same. If the means were identical, then yes, you could just look at standard deviation. The means aren't the same. All right, so what's machine X?
12, sorry.
1.2.
Yeah.
Oh, no, it is 12. You're right. Sorry, it's 12. Multiplied by 100, not 10. And what's the machine Y?
10.
It's 10. So which one's more consistent? The Y, machine Y is more consistent. What do you notice about the symbols they used for these? These are samples. These are not populations. Okay. Would they ever be able to get the entire population? They would literally have to look at every single bolt this machine ever made, right? To get it. Probably impractical. So what they do actually is, and what the inspectors and stuff will do, is they'll go in and they'll grab pockets of them at different points, and then they do this to figure out what the variance is. Okay, and then based on that, they have a table that says, okay, it's got to be within 10% or 5% or whatever else it is. And if it's outside of that, they have to shut that machine down to fix it. And it's the same thing for your food products. It's the same thing for medicine. Everything has a specific number that that variance has to be within. And they literally do this little calculation to figure that out. Now they have a nice little computer that does most of it for them, but this is how they actually figure that stuff out. Okay. All right. Questions? You should be able to finish all of chapter 4 stuff now. Okay.
What should we have for next spot? Like ready for
Your brain and a pencil.
like, I know
No, like honestly, so actually, this is actually a very good question. So next class, all I am literally going to do is review the test that's in Hawk.